Okay, let's continue to talk about continuous random variables. As we know, some random variables are continuous. Okay, in that case, we know the value of the continuous random variable is basically measured instead of being counted. Some examples we discussed in the past is that, for example, the number of students in our classroom when the next lecture starts would be discrete, right? This is because that we can count how many students do we have. Either there are 5, either there are 10. That number is counted, so that's a discrete random variable. However, for another thing, the temperature of our classroom at that particular time point would be continuous. Okay, that may be 20, that may be 20.5, that may be 11.7, that may be actually 19.345, whatever. That number can actually be anything, and that quantity is measured instead of being counted. So the temperature would be a continuous random variable. For a continuous random variable, the possible values typically lie in an interval. Okay, so there may be a lower bound, there may be an upper bound, and within the two bounds, all the values are possible. Okay, that's typically the case. So, for example, let's talk about that temperature example. Let X be the temperature in Celsius of our classroom when the next lecture starts. Then probably we can say X has the lower bound 0 and upper bound 50, okay, because it's basically impossible for the temperature to be below 0 and above 50. Okay, if that's the case, yeah, I guess it's the end of the world. So rationally, we would believe that X should be, for example, within this. Okay, so we can set a range for our random variables, especially for continuous random variables. Then for each value, each real number within this range, there is some likelihood for that to happen. When we have a continuous random variables, again, we are interested in knowing some quantities, like what's the probability for the temperature to be 20? What's the probability for the temperature to be within 18 degrees to 22 degrees, to be above 30, to be below 12, etc. Okay, we may be worrying or caring about these probabilities. So let's first introduce how these may be calculated. As another example for continuous random variables, consider the number of courses taken by a student in this semester. Okay, suppose we are talking about our class, and in our class we have let's say n students. Okay, we know n is around 35, 40, and for each student, we randomly pick one student and call it student I. We use xi to denote the number of courses taken by this student. Then of course xi would be discrete, maybe 4, maybe 5, maybe 3, or maybe some other numbers, but that number is counted. Okay, no problem. However, this is very important. The mean of all these numbers, okay, the mean of all these numbers is basically continuous, right? When we talk about each number, is 3 or 5 or 4 is discrete. The sum of them, again, is discrete. But when you divide the sum by 35, by 40, or especially by a very large number, then the possible numbers, the number of possible values would be very large. Okay? And the possible values of the mean would be some very fractional values, and the number of possible values would be very large within a certain interval. Okay, in that case, we basically say, okay, that number is approximately continuous. In statistics, as we will see very soon, the understanding of continuous random variables would be much more important than that for discrete ones, mainly because, for example, this guy, the sample mean, or many other statistics are treated as continuous random variables. Okay, that quantity is measured, calculated, instead of being counted, right? So that's why we really need to talk about these weird continuous random variables. Okay, good. So let's start with some very basic examples. Suppose now I want to randomly generate a value within 0 and 6. Okay, somewhat similar to rolling a dice. But when you roll a dice, the number would be either 1 or 2 or up to 6. You have 6 possibilities. But now I want to get a value within the interval 0 to 6. Okay, so any number within this interval is possible. So basically I have infinitely many possible values because I know my random variable now is discrete. Okay, so that's called the outcome of this generation being x. So x would be my random number generated from this interval. And let's say all the values in this interval will be equally likely to be observed to be our value of x. Okay? When we say I want to randomly generate a number within a certain interval, that means all the numbers within that interval has the same possibility to be observed. And that's why we say it's randomly, with no pattern. Okay, if now that's the case, let's consider the first very important question. What is the probability of getting, for example, 2? Okay, 2 is just an example. In fact, what I'm going to tell you would be applied to any single number. So let's talk about this. What's the probability of getting 2? Well, let's think about this. In fact, all the possible values may be an outcome, right? And how many possible numbers do we have? Well, the outcome may be 0, the outcome may be 1, 2.4, a very weird fractional number, an infinite fractional number, pi, square root of 2, etc. It's obviously true that we just cannot enumerate all the possibilities. Okay, there are infinitely many possibilities. So the probability of getting exactly a number would be 0, because in front of you there are infinitely many values and you randomly pick one. The probability for you to randomly pick this one would be 0. Okay? If that's a positive number, then the sum of all the probabilities would be greater than 1, right? And that's impossible. Okay, so now you know, when you want to draw a number for a continuous random variable, okay, draw a number within an interval, then for each single value, that probability is 0. Okay, it's just impossible for you to say, hey, with some probability, I'm going to see this number or see that number. That's just impossible. Okay, so in general, the probability for a continuous random variable to be exactly a number would be 0 for all the possible numbers, okay, for any number. So starting from now, when you are thinking about a continuous random variable, keep this in mind, okay? Any single value generates 0 probability, okay? However, some other things are different. It makes sense to ask what is the probability of getting no greater than 2. Okay, the probability for x to be no greater than 2. Let's look at this. So we're talking about generating a number within the interval from 0 to 6. Okay, from 0 to 6, all the single values have the same likelihood to be observed. Okay, from 0 to 6. Then when we say I want to get a number that is smaller than 2, then from 0 to 2. 0 to 2 has dense 2, and 0 to 6 has dense 6, right? So intuitively, the probability of seeing a number that is smaller than 2 would be 1/3. Okay, because this interval, the length is 1/3 of the total length of the possible interval. So when you randomly pick one number, with probability 1/3, it would be within this interval. Similarly, for any other numbers, you can do the calculation in the same way. If I want to ask what's the probability for x to be less than 3, 3 is the midpoint between 0 and 6. So the probability for x to be less than 3 would be 1/2. For probability of x to be greater than 4.5, it would be 1/4 because the length between 4.5 to 6 is just 1/4 of the total length. For the probability for x to be within 3 and 4, that's 1/6. Okay, 1/6 because again the total length is 6 times longer than the length between 3 and 4. So as a quick summary, for a continuous random variable, a single value has no probability. But when you talk about an interval, the probability for your x random variable to be within an interval, that's a question that makes sense because that can give you a probability. Okay, that can give you a probability. So very quickly, let's do another example. Suppose y is another random variable within 10 and 50. And again, suppose all the values would occur with the same likelihood. Okay, so I'm going to very quickly draw a line from 10 to 50. That directly means the total length of my interval, 10, 50. Then when I want to calculate the probability from 0 to 30, well, it doesn't matter whether it's from 0 to 30 or 10 to 30 or negative 1000 to 30 because y would be only possible to be above 10. Okay, so when I say this, all I am looking at is from 10 to 30. And you know 30 is the midpoint between 10 and 50. So the probability would be 1/2. Okay, when you talk about the probability for y to be above 45, then 45 would be somewhere here, right? So the probability for x to be above 45, you can do the calculation easily. The numerator would be the length that you are interested in. In this case, that's 50 minus 45. And the denominator is again your total length. So now it's 5 over 40, and that's 1 over 8. The probability for y to be within an interval 20 to 30 can be calculated again in the same way. You can see that it's simply 10 over 40, and that's 1/4. Finally, if you really ask what's the probability for y to be less than or equal to 5, because 5 is lower than 10, right? And x may only take values between 10 and 50. So this particular probability obviously should be 0. Okay. In general, we can give you a formula. Given any numbers a and b within 10 and 50, the probability for y to be within a and b can be calculated in this way. The length of the interval that you are interested in over the length of the total interval. That's the general rule. In fact, the random variables x and y, they are very special because we give you an interval of possible values, and all the possible values are equally likely to occur. So they are some kind of special cases, right? Because when one number is within an interval, it's possible that the value may be more likely to be here or there. No one says it always would be the same probability or the same likelihood. So x and y, these kind of random variables are special, so we give them a special name. For a continuous random variable of this property, okay, equally likely, all the numbers are equally likely to occur, we say it follows a uniform distribution, or we say its probability distribution is uniform. Okay, uniform means all the values have the same likelihood to occur. If we are talking about discrete random variables, for example, rolling a fair dice, right? We would say it follows a discrete uniform distribution. So now you have some special names for special distributions. You probably want to ask, well, when would we use a uniform random variable? At least we have two examples. First, when we want to draw one number from a population fairly, okay, that means randomly. For example, if today I want to give $1,000 to one of our classmates, then if I want to do that in the fairest way, I will say, okay, I'm going to randomly pick one. If I want to randomly pick one, then that's basically doing a uniform distribution. Okay, so that's useful. Of course, then in that case, we are talking about discrete uniform distribution. Or when we similarly say, when we want to do some sampling from a population, then in many cases, we want to make sure that all the entities within this population would be having the same probability of being selected. In that case, it's again an application of uniform distribution. Okay, so that's our first part of introduction of continuous random variables. You know there's one thing special, that is a uniform random variable, and you know the basic ideas. Single values have no probability, and for intervals you can calculate probabilities. Okay, thank you.